Hello everyone, my name is Clarita. I'm from 11 IPA and today I'll be teaching you guys about thermophysics. But before I start, let's learn the keyword for this topic. The first keyword that we're going to encounter is heat, which is the transfer of energy. The second one is thermal energy. That's the energy generated and transferred by heat, which refers to an internal energy or the average kinetic energy caused by collisions and movements of particles or molecules. The third, we have temperature, which is the measure of thermal energy being transferred that refers to the degree of hotness or coldness of a body. Now, after that, let's learn the first topic for today, that is temperature. But before I start, I have a question for you guys. What instruments or tools do we use to measure temperature? Anybody? Now, if you answer thermometer, then you're correct. Thermometer can be classified into two. The first one is according to its usage. There's the clinical thermometer, laboratory thermometer, and atmospheric thermometer. The second one is according to the liquid that is used. I'm sorry, there's a typo here. It's supposed to be alcohol thermometer and mercury thermometer. Now, currently we know a lot of different types of thermometer. But for temperature, we have many different units. Now, let's learn 5 for today. The first one that we're going to learn for today is the Celsius scale, or degrees Celsius is found by Anders Celsius, with freezing point at 0 degrees, boiling point at 100 degrees Celsius, and a range of 100. Remember guys, range is boiling point minus freezing point. I repeat once more, range is boiling point minus the freezing point. The second scale that we're going to learn is the Fahrenheit scale, or degree F is by Gabriel Daniel Fahrenheit, with freezing point at 32 degrees Fahrenheit, boiling point at 212 degrees Fahrenheit, and the range of 180. The 3, we have the Kelvin scale, or simply K, by William Thomson or Lord Kelvin. They are both the same person, so do not fret. The freezing point is 273 K, the boiling point is 373 K, with the range of 100. The fourth will be the Réaumur scale, or degree R, by René Antoine Foucault de Réaumur, with freezing point at 0 degrees, boiling point at 80 degrees Réaumur, and range of 80. The fifth, we have the Rankine scale, or simply R, by William John McCorn Rankine, with freezing point at 492 R, boiling point at 672 R, and the range of 180. Now, be careful not to get this mixed up. Réaumur scale has this tiny metal dot on the upper left side, while Rankine doesn't have it, so please don't mistake this, okay? After that, let's learn how to convert the temperature from one unit to another unit, and this is the formula. Now, the formula is T, which is the temperature that we are trying to look for, minus the freezing point over the range. Now, I have given you guys 2 examples. Now, let's guide you through one by one. The first one is convert 595 R, or Rankine, to degrees Celsius. Since we want to find Celsius, we put T degrees Celsius minus 0 over the range, which is 100, is equal to, since we know the given is the Rankine, so temperature Rankine minus the freezing point is 492 over 180. Since 100 and 180 can be further simplified, let's simplify it into 5 and into a 9. Now we can cross multiply it, and we shall get 57 degrees Celsius. Now, the second example is convert 95.5 degree R to degree Fahrenheit. Trying to find the Fahrenheit, so T degree F minus 32 over the range is equal to 95.5 degrees Réaumur minus freezing point 0 over 80 the range. Simplify it once more, cross multiply, and we will get the temperature is 246.87875. Now, since it's At temperature, it's best that we just round it up. So from this to 247 degrees Fahrenheit. Now, this is a very small topic, but it is included in our textbooks, and I want to further discuss it with you guys. Now, this is how to calculate temperature with mercury thermometer. Theta, which is the temperature, is equal to L theta. There's like small line over here. It's probably not really visible, but it's L theta minus L0 over L100 minus L0 times 100 degrees Celsius. Now, into the question, so it will be much easier to understand. In an unmarked mercury thermometer, the length of the mercury thread is L0, which is the length of the thread when it's in 0 degree, and the length of the thread at 100 degree are 5.0 centimeters and 25.0 centimeters respectively. What is the temperature theta when L theta is 14.0 centimeters and B 3.0 centimeters? Now, as I've stated before, the L0 is 5.0, L100 is 25.0. Now, let's answer A. When L theta is 14.0 centimeters, we take the formula and then we input the number one by one. So L theta is negative 14.0 minus 5.0 over 25.0 minus 5.0, and then we times by calculator, times by 100. You can do it directly in your calculator, and we will get 45 degrees Celsius. Now, at B, we also apply the same rule, same formula, just change up the number from from 14.0 to 3.0, and we would get negative 10 degrees Celsius. That's how you calculate temperature with mercury thermometer. Into the next subtopic. The second one is calorimetry. What is calorimetry, you asked? Calorimetry is the act of measuring changes in the state variable of a body for a purpose of deriving the heat. Also, the process of measuring the amount of heat released or absorbed by a physical or chemical system. Now, there are 4 units of heat in calorimetry. There's calorie, cal, which is amount of heat needed to raise a temperature of 1 gram of water by 1 degree Celsius. Kilocalorie or kcal is 1 kilo of water by 1 degree Celsius. Joule or J is 1 kilo of water by 1 Kelvin. British thermal unit or BTU is 1 pound of water by 1 degree Fahrenheit. Now, this part is very important, so I hope you guys will remember this part. This is 1 kilocalorie is equal to 1000 calorie. 1 calorie is 4184 joule, and 1 BTU is 1055 joule. Okay? We're going to skip this because I want to expand on specific heat capacity, or simply C first. What is specific heat capacity? Specific heat capacity is the amount of heat needed to raise or lower the temperature of a given mass of a substance by a certain temperature. Now, this little table over here would be provided to you test, so you guys don't need to memorize them at all. Now, with this in mind, let's answer the previous slides, shall we? Now, in this question, we have a 4 kilo rice at 15 degrees Celsius started to increase its temperature to a negative 2 degrees Celsius. How much of BTU of heat is absorbed by the ice? Let's write the given, so it will be much easier for us later. We know the mass is 4 kilo. Initial temperature is negative 15 degrees Celsius. The TF is negative 2 degrees Celsius, and the C is from ice, so it's 200 at 20,935 per kilogram degrees Celsius. The formula is M times C times delta T, which is input all the numbers one by one, and we would get 1,088,620 joule. Now remember, they say in BTU, so we must convert it. Remember, I said 1 BTU is equivalent to 1055 joule. So we put 1055 joule below, so we can cancel the joule out. So 1,088,620 divided by 1055, we will get 1051 BTU for the answer. Now, there are several effects of the heat. In this one, we would only focus on the length and on the volume. They would cause the change in length and the volume. Although area can also be changed, but linear and volume expansion is the one that we'll be focusing on today. Now, what does this triangle letter mean? Now, here's what it means. Delta L, delta A, and delta B is the change in the length or area or the volume, while ABY, or simply, since this is a laptop, it's hard to write. The symbol should be alpha, beta, and gamma, which is the coefficient of linear or area or volume expansion. This one would be provided during the test, so don't fret about it, or it would be given in the question itself. Now, the L0 or the L0, A0, or V0 is the initial length or the area or the volume. Delta T is just the change in temperature, which is final temperature minus the initial temperature. Now, this is what I meant by it would be supplied in the test itself. See? Linear expansion, solid, linear expansion, liquid. Now, let's proceed to the question. An 80 milliliters of CH3OH has a temperature of 35 degrees Reaumur. To what temperature is Reaumur must it be heated so that it will be 80.5 milliliters, given that its coefficient of volume expansion is 1.19 times 10 raised to negative 3 per degree Celsius. Let's write the given again. V0 is 80 milliliters. The V, it would be 80.5 milliliters. And the gamma is 1.19 times 10 raised to negative 3 per degree Celsius. And the thing that we are trying to find is the final temperature. But first, for it to be easier for us, let's change the 35 degrees Reaumur to Celsius with the conversion formula. Since we're trying to find the Celsius, T degrees Celsius minus 0 over the range 100 is equal to the provided 35 degrees Reaumur minus 0 over 80. Cross multiply and we will get 44 degrees Celsius. Now, for this particular question, we will be using this set of formula, which is V is equal to V0 times 1 plus gamma times delta T. Now, since we want a delta T or final temperature specifically, let's remove what we can. But first, we can divide this by V0, so V over V0, and then we can transfer the 1 to the left side, so it becomes negative 1, and we can now also divide this by gamma, and we can expand this to final temperature minus initial temperature. Since the thing that we're trying to find is the final temperature, we can also transpose this initial temperature to the left side. Now, with this formula, we will find what is the final temperature for now. So, insert the number once more, 80.5 over 80 per 1.19 times 10 raised to negative 3 minus 1 plus 44, and the final temperature would be 49.3 degrees Celsius. But it was asked in what temperature in Reaumur, so we have to convert it back again. So T degrees Reaumur minus 0 over 80 is 49.3 degrees minus 0 over 100. Simplify to 4, simplify into 5. cross multiplication, we get 5 PR is equal to 197.2, and the it would be 39.4 degrees Reaumur. Now you guys might ask, didn't you just say you have to like round it up? Yes, but in here we have to follow the rule, because see here there's like 3 significant figures, the significant figure rules. Okay. The next topic that we're going to learn is the latent heat. What is latent heat? Latent heat itself is the energy released or absorbed by the substance during a change of the state without a change in the temperature. So, when water vapor releases heat, it will start to condensate and turn to water. Water releases even more energy and it starts to freeze and it becomes ice. Same thing will apply. If ice receives heat, it will start to melt and turn to water. Water receives even more heat, will start to vaporize and becomes water vapor. With that in mind, we can do this diagram over here. Now, there's 3 stages here: solid, liquid to gas. The part where it starts to go up share the same formula, which is Q is equal to M times C times delta T. But there's the region here, this 2 region over here, where the line just is constant. That means it's like in the liquid state, like from solid slowly turn to the liquid state. Now, this period over here is called the latent heat of fusion, which is melting. LF is equal to M times LF. And the latent heat of vaporization, or simply vaporize, at LV is equal to M times LV. Now, these two, it's similar, but also different at the same time. So please remember these 2 formulas. Now, here are some table of LF and LV of various substances. And see this number, it may look small, but remember, this is a KJ. That means if we want to turn it into simply J, we have to add another 30 over here. And this is basically the melting point and the vaporizing point. With that in mind, let's start the example question. A 5 kilogram of acetic acid at 5 degrees Celsius is exposed to the heat until it reaches a temperature of 20 degrees Celsius. How much total BTU of energy is required in order to reach that temperature? Now we want to find the Q total, the total heat. With that, we can write the given, which is M is equal to 5 kg, initial temperature is 5 degrees Celsius, final temperature is 20 degrees Celsius, the C is 2180 J per kilogram degrees Celsius, LF is 192,000 J per kg. Let's do from, since this is acetic acid, the melting point is at 17 degrees. So Q1 is equal to M times C times delta T. Input each of the number inside of there and we get the result. Same thing to the LF, but in LF, remember, the formula is M times LF. And the LF is already given, so 5 times 192,000, and we will get 960,000 joule. Q2, the same thing, M times C times delta T, and we'll get 32,700 joule. With that, let's start to add all of them up, and we would get this result over here. Now, since this is still in joule and we need it to be in BTU, we can convert it by dividing it with 1055, cancelling the joule in the process, and we get 1065 BTU for this answer. Now, the last but not least, the heat transfer. What is heat transfer? Heat transfer itself has 3 types. The first one in conduction. Conduction is the process in which the heat energy is transmitted through the collisions between neighboring atoms or molecules. This happens more in solids and liquids because the nature of them having a much closer distance in terms of atoms or molecules compared to gas, which is very loose. The distance between them is very loose. The common example that we can find in our daily life is like pots, pans. This is a solder. I think you guys can find it in tech shop, usually phone stores. And they are both made of steel or metal because some metals are a very good conductors. Remember, conductors. While other not so good conductor materials such as wood, cloth, and etc. Second, we have convection, which is the transfer of heat related to the movement that occurs within a fluid due to the rising of hotter materials and sinking of the colder ones. This is because the hotter ones have a less density than the cold. The common example for convection can be found in our kettle or electric kettle and our aircon. And today I'll be discussing the convection happens in the kettle, while you guys can write or the principle, the convection principle behind the aircon, okay? After that, we will check it tomorrow, okay? Now, I'm sorry for saying too much, okay? Okay, I did it again. So, when we are heating water inside a kettle, the source of heat is from the bottom down here. And since the water in this region is directly touching the source of heat, of course it would be the first thing that's starting to get hot. After that, the hotter water would start to rise up and the colder will go down because density once more. And this process would repeat itself until all of the water here are all hot, basically. So when you try to see a boiling kettle and you took off the lid, you can see the water starts to swirling around because of that principle itself. The third one is radiation, which is the transfer of heat via electromagnetic wave. Unlike conduction and convection, this doesn't require any medium to work at all. Now, this can even work normally or even in space or vacuum. The first one is our sunshine. Like, the sun is millions upon millions kilometers away from us, but the hotness can be seen, can be felt by us even though we're so far away. This is because it can work even in vacuums, while in bonfire, the heat would starts to it travels via the air. That's why the heat can reach us, and that's the principle. That's the radiation. And so that's all for today, guys. I hope you guys understand what I meant. If I have said something wrong or I mispronounced something, I am sincerely sorry. And if you guys have further questions, my DMs or my private chat is open. You guys can ask me directly, and I would answer to my utmost knowledge. Okay? Goodbye, and thank you, everyone. Have a nice day.